Have you ever wondered how we see the world around us? Think all the beautiful things like flowers, fish, plants, animals, a vibrant environment full of colors. If you haven't, then let's take a journey to discover this together in this lecture. Imagine you're outside on a bright sunny day. Light from the sun is shining all around, making everything come alive with color. But here is something amazing. Sunlight isn't just one single color. It has made up of many different colors like a rainbow, consisting red, orange, yellow, green, blue, indigo and violet color. The range of light we can see stretches from about 400 to 700 nanometers. Now let's explore how we actually see things like a banana or an apple or any object. As we have discussed, any white light consists of 7 different colors. When this light incident on any object, suppose here it incident on an apple, it absorbs all the colors and reflect one color, and that is red in case of apple. When this red color goes to your eyes, and then a series of events occurs in your eyes, and through the optic nerve the information goes to your brain and you can detect the color and the image. So here the apple absorbs all the colors but reflect the red color, which have wavelength about 620 to 750 nanometers. That's why the apple looks red to you. A banana on the other hand reflects yellow light and absorbs all other color, which has a wavelength of 570 to 590 nanometers, making it appears yellow to your eyes. White objects reflect nearly all wavelengths of visible lights. They bounce back almost all the colors that hit them, which is why you see a mix of all colors when you look at something white. Black objects, however, absorbs most or all wavelengths of visible light, reflecting very little black. That's why they appear black. There is minimal light reaching your eyes. But here is the real question. How does this reflected light actually create the image we see? Well, this is where the concept of isomerism comes in, and it's truly fascinating. Let's dive into it. When the reflected light from an object enters your eyes and ultimately triggers an impulse that travels to your brain via the optic nerve, allowing you to see the apple color. But how is this impulse generated? When light reaches to the retina, the back layer of your eye, it encounters a special cell called as the photoreceptor cells. There are two types of cells, that is the cone cells and the rod cells. Cone cells allows us to see the colors, while rod cells helps us in the low light. Now, without going too deep into the biology, here is the key thing. The cells contain a special organic molecule called retinal, which is vitamin A derivative, as you can see here. In the natural state, retinal exists in the bent form known as the cis-retinal. When a photon of light strikes this cis-retinal, it delivers just enough energy to create a dramatic change. This is where the magic of isomerism happens. A retinal molecule flips from its cis form, that is the bent form, to a straight form called as the trans form, as you can see here. In this structure, you can see the two hydrogen are in the cis position, but here you can see two hydrogen are away from each other in a trans position. Dear student, look at this beautiful molecule. This is cis-retinal. Here you can see at this position, two hydrogens are on the same side, so this molecule is called as the cis-retinal. Real magic happens when reflected lights goes to your eyes. That light is used to break this particular bond, this pi bond, and once this pi bond is broken, there is a conformational change, and again the bond is formed. So here you can see the cis form is converted into the trans form. Now two hydrogens are away from each other. Here, this change is very crucial as it generates an electrical impulse that travels through the optic nerve to the brain. Once the information reaches the brain, trans-retinal is converted back to the cis-retinal, allowing the cycle to repeat. This conversion from cis to trans happens incredibly fast, in about 200 femtoseconds, almost instantly after absorbing a photon of light. And this rapid transformation is an example of isomerism, which is exactly what we are diving into today. Here you can see cis-retinal. In the presence of light, it converts into the trans-retinal. Now, as you can see both molecules, cis-retinal molecular formula is C20H28O, whereas the molecular formula of the trans-retinal is C20H28O. Now, you can see they both have similar molecular formula. Then why these two molecules are different, right? So, the molecules which has same molecular formula but different physical and chemical properties, such molecules are called as the isomers. And this is the topic of interest. Now, in this lecture, we will understand what exactly isomerism is. Here, you can see two powder forms. They are looking similar. Even both have same molecular formula, that is C6H12O6. But the first one is called as the glucose and the second one is called as the fructose. Such compounds which has same molecular formula but different physical or chemical properties are known as the isomers. Isomerism.
The term isomer was coined by the Swedish chemist Jöns Jacob Berzelius in 1830. In the early 19th century, Berzelius was studying tartaric acid and racemic acid. These acids have the same molecular formula but different properties. He realized that there must be a structural difference causing these distinct properties. This observation led him to propose the idea of isomerism, where compounds can share the same molecular formula but differ in the arrangement of their atoms. His work laid the foundation for the concept of structural isomerism and paved the way for further discoveries in the field of organic chemistry.
Term isomerism consists of two words. Iso means same, mer means unit. Two or more than two organic compounds having the same molecular formula but different physical or chemical or both properties are called isomers, and this phenomenon is called as isomerism. Isomers have same molecular formula, they have same molecular weight, they have same double bond equivalent, they have same vapor density, and they have same percentage of element. Even they have same empirical formula. Now, what is empirical formula? It's the simplest ratio. For example, C6H12O6 is a molecular formula of glucose. If we make it simple, it will be like CH2O. This is called as an empirical formula, which is the simplest ratio. So, two isomers have same molecular formula as well as same empirical formula. Isomers have different physical and chemical properties, and this is very much important. They also have different IUPAC name. Now here we took two different examples. IUPAC name of the first one is ethanol, that is ethyl alcohol, and second one is the methoxymethane, that is dimethyl ether. Both have same molecular formula, that is C2H6O. They both have same molecular weight, that is 46.07 gram per mole. They both have same double bond equivalent, that is 0, as there is no double bond as well as there is no ring in the molecule. Ethanol exists in liquid state, whereas dimethyl ether exists in the gaseous state. Boiling point of ethanol is 78.5 degrees Celsius, whereas boiling point of dimethyl ether is minus 23 degrees Celsius. When ethanol reacts with sodium metal, H2 gas is released, whereas dimethyl ether with sodium metal does not show any reaction. So here you can understand ethanol and methoxymethane have same molecular formula, same molecular weight, same double bond equivalent, but they have different physical and the chemical properties, as their boiling points are different, their physical states are different, chemical reactions are different, as well as their IUPAC name is also different. So here from this example you can understand what is the meaning of isomerism. Let's see reaction of sodium metal with these two examples. When ethanol reacts with sodium, sodium ethoxide is formed and H2 gas is released. Here you can see. When dimethyl ether reacts with sodium, it do not show any reaction as there is no acidic hydrogen in the molecule. Clear? So they have different chemical properties. Here we have enlisted physical and chemical properties. Please pause the video and read carefully. This will help you to differentiate between physical and chemical properties. Now let's solve one question. Isomers must have same, option number 1 is structural formula, physical properties, chemical properties and molecular formula. So what is the answer? They have same molecular formula. Very good. Note, are CH4 and CD4 isomers? Please think. Yeah, hydrogen, deuterium, tritium are the isotopes, right? So I think they may be the isomers of each other. Let's have a look. Hydrogen, deuterium and tritium have same atomic number but different molecular weight. If you calculate the molecular weight of CH4, it will be 16 and CD4 it will be 20 gram per mole. So as we have discussed, isomers must have same molecular formula as well as they must have same molecular weight. So here you can clearly see that the molecular weight is different. So here you can clearly see CH4 and CD4 are not isomers of each other. So this is very important point, my dear students. Isomers are broadly classified into two types. Number one is the structural isomers and second one is the stereoisomers. Structural isomers are also called as the constitutional isomers, whereas stereoisomers are space isomer or 3D isomers. Structural isomers are further classified as chain isomer, positional isomer, functional isomer, metamer, ring chain isomer and tautomer, whereas stereoisomer are classified as conformational isomer and configurational isomers. We will see what is the actual difference between conformational isomer and configurational isomer. Now students, quickly understand what is the difference between conformation and configuration. Let's take one molecule. Suppose this is an ethane molecule. At room temperature, this molecule is continuously rotating. There is a free rotation between these two bonds. So you can see different conformation at different intervals, right? This is called as conformation. Now, to understand what is configuration, let's take one example. Here you can see the carbon-carbon are connected with two bonds. That is one sigma, one pi bond. There is a clearly restriction in rotation. Now you cannot rotate these particular bonds, right? So if you have to change their position, suppose this is Cis-Trans CH3 group. Now if you have to change their position, only one option you have, that is you have to break the bond. So here you can see by breaking the bond, now the position is changed, right? So dear student, what you have studied, in the conformation, molecule can rotate about their single bond without any disturbance at room temperature. But in configuration, you have to break the bond to change their arrangement. Clear? Configurational isomers are again classified as geometrical isomer and optical isomer. This is the entire classification of isomerism. That is what we have to study in this particular course. Structural isomers have different IUPAC name. That means there must be a difference in the connectivity between the atoms. Whereas in the stereoisomers, the atom have same connectivity. They have same IUPAC name, but there is a difference in the 3D arrangement of atom in the space. Suppose in the ethanol, you can see oxygen is connected to the hydrogen and on the other side it is connected to the carbon. So there is carbon oxygen hydrogen linkage. Whereas in the dimethyl ether or methoxymethane, you can see oxygen is connected to the carbon on the one side and on the other side it is also connected to the carbon. Here COC linkage is there. So you can see there is clear difference in the connectivity between the atoms. So they have different IUPAC name. So ethanol and methoxymethane are called as the structural isomers. Clear? Now to understand stereoisomerism, let's take a simple example, but2-ene. It may exist in two different forms. In the first orientation, you can see two methyl groups are close to each other in the same side. Whereas in the second orientation, two methyl groups are present away from each other in the opposite side. You can note length between methyl and methyl in the first orientation is L1, whereas length between methyl and methyl group in the second orientation is L2. So there is a clear-cut difference between the length L1 and L2. That is, L1 is not equal to L2. Clear? Here, between these two orientation, you can see they have same molecular formula. They have same IUPAC name, that is but2-ene. They have same connectivity, but there is difference in the 3D arrangement of atom. And those isomers are called as the stereoisomers. I hope this is very clear to you.